going to be doing homework 2, part B. So the first question is express the heat diffusion equation from part A1 as an algebraic equation via the Crank-Nicolson differentiation. So our heat diffusion equation is dT over dt, the thermal diffusivity, over the second derivative of temperature and position. So what we had was our algebraic form of the heat diffusion was, algebraic form of our heat diffusion is going to be Tj n equal plus 1 Tj n plus R, and then parentheses, times Tj minus 1 n minus 2 times Tj n minus Tj plus 1 n. So this is our algebraic form of our heat diffusion equation. Revision is, this is going to be negative, and this one's going to be positive. So for our Crank-Nicolson equation, what we want to do is we want to find the average of the current time and then the average of the time plus 1, right? So we are going to take the average of this equation. So the average of this equation is going to be Tj n plus 1 equals Tj n plus R, and then we're going to do is brackets. So then we have our Tj 1 plus 1 minus 2 Tj n plus 1 minus Tj n plus 1, and then we're going to add that. This is going to be all over 2 because it's an average, and then we're going to do Tj plus 1 n minus 2 Tj n minus 2J n. Okay, so this is our average of this equation here. So that is going to be the end of part 1, because this is our Crank-Nicolson. So our part 2 for homework 2 is going to be, we're going to use the von Neumann stability analysis to show the Crank-Nicolson differentiation scheme is stable regardless of the choice of R. So what we used in part 4A, we did Tj n plus 1 equals Tj n plus R, and we had our E's, right? So for the stability, we had e to the ik delta x Tj plus 1 n minus 2 Tj n, and then we had minus e negative ik delta x, and then we had Tj minus 1 n. So this is our equation that we had for the von stability. So what we want to do to make this Crank-Nicolson is we want to take the average again with our 2 time steps, so the time step that's at currently and then the time step that we have later on, right? So to change this, we are going to use is Tj n plus 1 equals Tj n plus R, and then we are going to have our 2 time steps. So it's going to be e to the ik delta CH, and then TJ n plus 1, and then n. So that's going to be our time step for the next time step, and then TJ n plus 1, and then E negative I k delta x of the TJ minus 1 H plus 1, and then this is all in parentheses, and then we're going to add this to the E. I'm going to move this down here, so then it's going to be in parentheses down here, it's going to be E I k delta x of the TJ plus 1, and then it's the current time step, and then 2 TJ n minus E to the negative I k delta x over TJ minus 1 n. And then that, so this is for stability, right? So next thing that we want to do is we're going to take it on both sides. We're going to separate these two, have one side be TJ n plus 1 and one side be TJ n. So I'm going to erase the top part. So we have this here, so I'm going to bring TJ over, so TJ n plus 1. So on this side we have all of this here, so TJ, and then it's going to be brackets, so 1 plus R. So this is going to be minus R, and then we're going to have, so E minus, so E I k delta x, and then minus 2 minus E negative I k delta x. And then this is in parentheses, and then this is going to equal our TJ n, and this is in 1 and R, and then we have it down here, so E I k delta x minus 2 minus E negative I k delta x. So the next thing that we want to do after that is we know from our previous, from part A, that these two E's make a cosine, make a 2 cosine, so we're going to do that on both sides since we can do that. So let's rewrite this. So I have TJ n plus 1, and then I have 1 minus R, and then I have 2 cosine of k delta x minus 2, and then I have this equals TJ n 1 plus R, and then cosine of x 2kx minus, 2 here, minus 2. Okay, so what do we want to change about this? Let's change so that this is negative, so that these are the same. So this turns to positive, this turns to negative. This turns to positive, this turns to negative. And then we have, on both sides, we have 2 minus cosine of k delta x. And over here, we are going to have this 2 minus cosine 2, this should be 2, should be 2 here, of k delta x. And then we're going to take out the 2's on both of those equations. So then we have TJ, I'm just actually going to just take it out and then we'll rewrite. So 2, erase, that's a 1, erase here, erase to 1, erase to 1. Okay, so now that we have this, we can put our R's over each other to see what we're working with. And yeah, so then we're going to have on this side, we're going to have TJ n plus 1. And then here, this is going to be TJn. And then we're going to divide. This is going to be top, this is going to be the bottom. So then we have is 1 minus 2r, 1 minus cosine of k delta x, all over 1 plus 2r, 1 minus cosine k delta x. Okay, so after we have this, we can call this term right here, so our 2r and then 1 minus cosine k delta x, we can call that our z term, right? So let's say this is our z term. And so then we have our tj n plus 1 equals our tj n. And so then if this is our z term, we have 1 minus z over 1 plus z. So if we think about this, right? So our cosine could be either, it goes from 0 to 1, right? So if this is 0 to 1 here, this is going to either be 0, this is going to either be 0 or 1, right? So knowing that, we know that this here cannot get bigger than 1. So we know that the bottom equation is going to, the numerator is always going to be less than the denominator. The numerator is always going to be less than the denominator. And because of that, we know that this will never go to infinity, right? So this is telling us right now that since this r here, right there, right here, that we can choose any r we want because this will not be undefined. So this gives us that we can pick any r we want and this will still be stable. So this is working for that. So that's the end for part 2. So part 3. So part 3, we're going to simulate a time-dependent response of a uniform bar initially at 20 degrees Celsius. After the ends are raised and maintained to 50 degrees and 80 degrees Celsius, respectively. We're going to discretize the bar into 100 time-dependent temperatures, and we're going to solve from part 1 using the SciPy line algebra solve banded, and we're going to use r is going to equal 2. We're going to do over 2,500 time steps, and then we're going to plot the simulated results. So the equation that we made in part 1 of B is that we had our average with the Crank-Nicholson equation of using the heat diffusion. So we're going to use that to help us make a matrix that will help us plot. So our first one is, it's not that. It's TJ n plus 1 equals our TJn plus our r. And then we're going to have our brackets, and then it's going to be our TJ plus 1 n plus 1 minus our TJ n plus 1, this is a 2, minus our TJ minus 1 n plus 1, and then plus our tj plus 1, and 2j, and minus tj. And this is all over 2, right? So after we have this, we're going to want to split it up in, so one side is going to be our tjn plus 1, and the other side is going to be our tjn. So our tjn plus 1 is going to be tj plus 1 Okay, so side of the equation is going, okay, so our left side of our equation is going to be negative rtj minus 1 and plus 1, and then this is going to be plus 2r plus 1 tj n plus 1 minus r tj plus 1 n plus 1 is going to be equal to our rtj n plus tr1 tj n plus 1 plus rtj plus 1 n. This should be just n. Okay, by the way. Okay. So after we have this, we can kind of highlight here. So we have our tj here, we have our j here, we have our tj here as well. So let's make our matrices with this information. So let's say we have a matrice here, matrice here and here, right? So this is j equals 1, j equals 2, j equals 3, and then this can go on till the nth term. And then over here we have our t1 n plus 1, we have our t2 n plus 1, we have our t3 n plus 1, and then this can go on for the nth term as well. So the first thing that we want to do is let's do our J2. So our J2 is, so if the position is 2 and we plug it in for this one, this is going to give us our T1. So our T1 is going to be equal to negative R. And then if we put our 2 into here, we'll get our times 2. So our T2, and that's going to be our 2R plus 1. And then if we plug this into here, this is going to give us our T3, which our T3 is negative R. And then we'll do J3. So J3. So if we plug our J3 in here, if we plug it into any of these, we won't be able to get our T1 because it's out of our bounds of our equation. So this will be a 0. So when we plug this into here, we'll have a T2. So our T2 is going to be here. It's going to be negative R. And then we'll have, we plug this 3 into here. This is going to give us our 3, so TR plus 1. And then if we plug this 3 into here, we'll get our 4th, so our T4. So I'm going to make a little room over here for that. So just so you know, that's R here. So that's our 4th term. And then if we do our J1, so our J1, if we plug this back into here, this is 0, so it's not going to be a term. And if we plug it into here, we'll have our 2r plus 1. And then we have, if we plug our j into this, we'll have our t2, so that will be negative r. And then if we plug this in, we won't be able to get a t3, so that will be 0. So that's out of our bounds. So just like this, you'll have our j like 4, 5, 6. We won't be able to have that because it's out of our bounds of our equation. And also in the problem, it says that we have our two ends of our bars. Our left side is going to be 50 and our right side is going to be 80 degrees Celsius. So we have to use our vector. So left TL, so our left is going to be 50, our T right is going to be 80 degrees. So we just have to keep that in mind. So when we do the multiplication for this, so let's do the second row. So the second row is going to be R T2. It's going to be R T2N, and then we're going to add, and that's going to be T2 minus 1 for this, and that's going to be our T2 N, and then plus our T3N. Okay, and then for our next one here, so let's do J3. So J3 is going to be our RT, and then this is the second one, so we're starting that. This should actually be 1 here. Our 2N plus our 2RN, 2R minus 1, T3N plus our T4N here. So that is for J3. So the next thing that we want to do is we have to account for our left and our right of our bar. So we have to add this onto it as well. So this is going to be so for our first one, it's going to be 2R. So 2 times R times RT left. And then we're going to do 2, in parentheses, 2R minus 1. That's T1N. And then we're going to have R plus R T2N. Yep, exactly. And then we have to still account for our right side of our bar. So down at the bottom corner of this, it would be negative R times 2R plus 1. And then we go over here and do the last line of our matrix C, and that is going to be accounting for our right side. So what we're going to do is 2R TJ. So we're doing the bottom line of this. So it's going to be our R times TJ minus 1 N. And then we have our, sorry, I touched that. And 3. So then we have our TJ and minus 1 over here. And then we're going to have our 2R minus 1 of TJN. And then we're going to account for our right side, which is going to be 2 times R right side here. So there's a diagonal with this matrix. It's not drawn correctly, so I can redraw this. So you can see the diagonal. So the diagonal goes 2R plus 1, negative R, 0, and then we have negative R, 2R plus 1, negative R, and then we have 0, negative R, 2R plus 1, and then we have 0, 0, negative R. Yep. And then we have just 0, 0, 0. So this is what it looks like. So there's a diagonal here with that. So we're going to do the coding part of this problem. I'm doing the coding portion for homework 2 part B. This is going to be for 3.
So I'm going to use the same code that we use for part A, and I'm just going to modify it. So the first thing that we want to do is we are going to import our new library. So from scipy.lineout, we're going to import solve banded. I think that's how you spell it. Okay. So we know from the example that we're using r is equal to 2. Our steps are going to be 100. This is right. We're going to change this to left, and then this is going to be right. So then after that, we want to kind of make our diagonal. So our diagonal is we're going to do mp.full, and we're going to have it as minus r and n minus r, and then we're going to have mp.full for our n, and it's going to be 2 times, and this is actually 1 plus 2 times. Okay, so then our diagonal is going to be, if we do sparse A, and we're going to do mp.c, so concatenate it, and then we're going to have our two diagonals for this. So it's going to be this. And then we want this to be the same size, so we're going to have to put .t at the end. Nope, just t. Okay, so after that, after we have our sparse here, so the next thing that we want to do is change our position. So it's going to be n plus 2, and that's because we have our left and our right values. And then the next thing that we want to do is we're going to change our scatter. So to do this, we are going to do is np.r underscore, and we're going to do is we're going to have our left and our right. So it's going to be left, t, and then right. So we account for all of our temperature values. So left, t, right. And then our modes are right, and that's correct. And then we know for our time steps, we're going to do is 1, and then it said in the prompt that it's 2,500. And so then we're going to change this in the middle here. So it's going to be b is equal to 1 minus 2 times r t times t. So then we have our b is going to, we're going to add our left and our right values. So b is plus, we want to add b to our values that are in the middle. So just have that is going to be plus equal, and we're going to have our, well, it's going to be 2, oh, shows the, it's going to be r times t. So the first one needs to be the second one. So it's starting at our second value. So then b and we want to add it to our last value as well. So yeah, 1 equal to our -2, so our last value that we know. And then we have to look at our first and our last value. Okay, which is our b is our 0, so it's going to be plus, equals, and then we are going to have is our r times t, and it's going to be our 1, and then it's going to be plus 2 times r left, and then b of -1. So that's our last value, is going to be r times t. -2 is our last value that we know, and then plus 2 times r times t right. And then how we can solve, so t is going to equal to solve banded, and it's going to be 1, 1, okay, it's going to equal 1, 1, and then sparse of our a, and then it's going to be b, which we just solved for. And that's it. And then we're going to change this to 100 because we're doing 100 times steps. And then we want to change this t to what we have right here. So let's see. Okay. So right here we have is, again, we have our 50 time steps right here. Goes up to 50, and it's all banded up to 100. And we have from 2,500. So this answers the end of homework 2 part B, and that is the end for homework 2.